Thanks for your introduction. I'm Chen, and this is Xiaowei. We are from Shandong University. Since Winhai is not able to attend the meeting due to visa issue, he asked us to say hello to everyone. In this talk, we discuss about a consistency-preserving word cloud editing tool, EdWordle. As many of you may have seen, Wordle is a cute and popular text visualization tool that converts a piece of text into a word cloud. However, Wordle is not editing friendly. For example, we often want to add or remove some words to a created word cloud. Unfortunately, Wordle doesn't support it. Recently, some researchers attempt to address this issue. For example, ManyWordle was developed to allow the user to move, rotate, and remove a word with a mouse. Wordle Plus extended ManyWordle to multi-touch settings and enriched it with natural interactions. This example demonstrates how ManyWordle facilitates the user to edit wordles. Here, we move the word Wordle. It's an easy operation, but you can see that some words fly to completely new places during this movement. This can be frustrating if you are also concerned about other words and don't want them to move. In fact, both ManyWordle and Wordle Plus can result in global and unpredictable layout changes. Our approach overcomes these limitations. We provide a system called EdWordle, which preserves a consistent neighbor relationship before and after editing. You can find it in this website. Let's see a comparison of EdWordle and ManyWordle. ManyWordle results in global and unpredictable changes, while EdWordle preserves neighborhood relations of words. For example, watch the word users. In ManyWordle, it jumps to the top of the layout. Also, the word visualization, it jumps away. That can be a problem if you do hope that Wordle, users, and visualization stay together during the editing. While in EdWordle, the neighborhood relation of these three words are kept. Let's see an editing demo. Sorry, let's go on. Okay, this is our website. I'll show some basic interactions like moving, rotating. Oops, there are some gaps. Don't worry, we have a function called ReWordle to solve this problem. And adding words. And multi-word interaction. You can find this demo on our website. Let's give a brief introduction to the related work. There are lots of work in word cloud visualization. In semantic word cloud, similar words are placed close to each other. All existing algorithms do not allow users to reposition words, which means that semantics cannot be adjusted once the layout is generated. Our neighborhood preserving method is specifically important for semantic word cloud. Now let's see the overall pipeline of EdWordle. The process starts by simply loading text that can be copied and pasted into the tool and applying the standard Wordle algorithm. We use our customized rigid body dynamics to move words close to each other. Now the layout becomes much more compact. The user can then freely edit the cloud until the desired result is obtained. Empty spaces are removed by using a local version of the Wordle algorithm. That's our overall pipeline. Now Xiaowei will explain details of the process.
Before talking about our technique, let me briefly introduce the background of rigid body dynamics. It studies a movement system of interconnected bodies under the action of external forces. Basically, it consists of two components, body representation and dynamics construction. In word cloud, people previously used boxes to represent words and added external forces to them, then detected collisions of their movement. One problem with a word-level box representation is that it leads to large empty spaces between words. To alleviate this problem, a possible solution is to use letter-level boxes. But in this way, words might overlap. For example, the letter I and O of the word nation cancel out each other so that the word delicate and the word nation get stuck. Instead, we employ two-level box strategy. It consists of two parts, the bounding box of the common part of all letters, and the letter-level box. This example shows the common part bounding box, and this one shows the letter-level box for each letter. So one can say that the word nation has 7 boxes in total. Since two-level box leads to larger computational cost, we use this representation only for words whose sizes are larger than certain threshold. That is to say, to be a compromise, we apply two-level box for some large words, and for other words, we use normal word-level box. To produce a compact layout while preserving the neighborhoods, we apply two external forces to word boxes, neighboring forces and central forces. Neighboring forces pull words close to each other, and central forces drag all words to the canvas center. To add neighboring forces to a word, we first need to find its neighbors. Connect the body center of certain word and all other words. If the line segment connecting these two words doesn't intersect with a third word, these two words are neighbors. As shown in the figure, the word with the red border isn't the neighbor of the selected orange word. Neighboring words with large distances can now be put together. So we introduce a central attraction source, a large mass at the center of the canvas to attract all words toward it. Finally, join the neighboring forces and central force together. Let's see the effect of these two forces. Here is the resulting word cloud after deleting the word conceived in the input word cloud. The result generated by only applying neighboring forces and only applying central forces. You may already notice that these two layouts are not compact enough. So we combine these two forces together. It is clear that the layout with joint forces is much more compact. Is it done? Not yet. You can find that the system is not stable. The words seem to be shaking. This is because directly applying forces to words will cause the system to halt. The words shake around at each iteration step. So how to solve this problem? The answer is to apply two damping strategies, force damping and velocity damping. Now you can see the shaking disappears. We're almost done, but still one more issue to deal with, gaps. Such gaps often appear at the boundary of a word cloud due to non-uniform spatial distribution. To fill them, we propose a local EdWordle layout algorithm. The algorithm contains two parts, identification of boundary words and picking the best position. The words immediately outside the circle are taken as boundary words and are shown with red borders. Several candidates are found of the word highlighted in orange, where the green circle indicates the starting position and the yellow triangle the position finally selected. Besides basic interactions like moving, rotating, we also design some cool interactions, such as adding words and multi-word interaction. And multi-touch version. Let's see this demo. This EdWordle comes from a BBC article about current international affairs. The user moves words to create semantic word cloud. And finally, she painted the words of the same issue into the same color. And here we compare the layout results generated by EdWordle and EdWordle after moving and rotate the word dedicate. In EdWordle, this editing step invokes global repositioning of the words marked with orange boxes and results in a non-compact layout. Our approach overcomes these limitations, retains word neighborhoods, and compactness of the layout.
Now let's talk about the evaluation of our method. We have done evaluation in 3 steps: quantitative comparison, lab study, and case studies. In quantitative comparison, we use other semantic word clouds layouts as input for EdWordle for further processing. We use 2 datasets, which contain 168 layouts of different articles in total. This figure demonstrates that realized adjacencies for the output layouts, which are represented by dotted lines, are almost equal to the original layouts, which are continuous lines. That means the neighborhood relations are well preserved by EdWordle. In the second picture, the input is the solid bar and the output is the dotted bar. It shows that the compactness of these word clouds is improved by EdWordle. Here's an example. We can see that the compactness of this Wordle layout gets improved substantially. Here goes the lab study. In this part, we compare EdWordle with ManyWordle. We invited 16 participants and defined the following procedure for the study. I'll just explain 2 tasks. Task 1 is pairwise movement, which intends to test simple and common interactions of word placement. For example, we asked user to put created on top of clouds, tag on left of using, and tool on top of results with a small angle of rotation. And let's see a good work of this task. We consider this result to be a successful one for the example task. Task 2 concentrates on correcting semantic misplacement. Here we put words of the same semantic group together and painted them into the same color. So now color represents groups. And you can see that some words are misplaced, like South, One, and Olympics. The user needs to move them to the right groups, like this picture on the right. The results of our quantitative measures are summarized in the 4 figures. All measures show a clear and strong effect of EdWordle being more efficient than ManyWordle. For example, the first figure comparing time users spend on tasks. The black line represents EdWordle and the gray line represents ManyWordle. We can see that in general, it takes less time for users to finish their tasks by EdWordle. In case studies, we invited 10 participants to our study. All of them worked in some sort of creative profession, such as graphic design or journalism. They used EdWordle to create a layout according to their own tasks and tastes. For example, this picture comes from the speech, "I Have a Dream" by Martin Luther King. The designer concentrates on the phrase, "All men are created equal." We were happy to observe that each of every 10 participants engaged in a very creative design process and came up with interesting and inspiring layouts for different texts. We believe that there are many other ideas that can be developed based on our consistency-preserving approach. For example, more cool multi-touch operations like pushing bar, automatically generating storytelling word clouds, and so on. That's nearly the end. More details can be found in our website. EdWordle is available online. Thank you very much for listening.